Thank you, and hello to everyone. First, I would like to introduce myself. My name is Abdullah Nasser. I'm a PhD student within the Computational Intelligence and Applications Research Group at Nottingham Trent University. Today, I would like to present my paper, and the title of my paper is A Novel Privacy-Preserving Approach for Physical Distancing Measurement Using Thermal Sensor Array. Yes, my main supervisor is Professor Lutfi, and Dr. Johnny Jong is one of my secondary supervisor as well. So I think the best thing to start with is the motivation of our work and why it is important. So as we know, all of you know that, for example, coronavirus, has several consequences, not only the illness itself, but also it has, for example, a damage in the economy. And even reported studies shows that there is an employment rate by 20%, which is again very high in normal circumstances. So I think this is actually a very important point. That I think if there is a social distancing measurement, we at the beginning we didn't go to this level of restrictions. On the other hand, COVID-19 is actually changing the virtual science, is changing to virtual science communication. And the evidence of this point is this conference that we are having now. We normally, what we are in normal life, you would be in a nice city, in a nice island, where we meet and discuss over a cup of tea, maybe in the break time. But because of what's happening, I think the uncertainty, again, COVID-19 changing the science to a virtual medium communication. And I think, in my opinion, if we had a good social distancing system that can trigger alert, we would be able, I think, to move. Anyway, I think there are other issues regarding this. So we are not claiming that we are the first people who develop a physical distancing system, but what we claim is we are proposing a thermal sensor array, which actually provides a low resolution thermal image and a framework that tolerate this output of the sensor to measure the physical distancing. Okay. So, the current work of the physical distancing system is actually was built on, or the purpose of it is actually, the aim of it, the main aim is actually easy to deploy systems. And what do I mean by this is, COVID-19 was a sudden action, a sudden event. Let's agree on this. And because of that, many people started to make kind of physical distancing system that is easy to deploy. We want to mitigate that sudden event as quickly as possible. And this leads to have serious performance and reliability issues in the existing work and research. And this is because the majority or most of the work was based on Bluetooth proximity sensor. Okay. There are also some work that use the camera, and I agree that the camera provides very good or very high performance in solving the physical distancing problem. But I think it has a very kind of consequences regarding the privacy of the user. I think because it violates user privacy, and I think no one of us accept to have kind of a camera in elderly home, or even elderly home or in nursing home. They don't like to, elderly people, they don't like to be monitored every time. I think using a camera is kind of has a very low acceptability from the stakeholders. Even if we want to have this system in hospitals or in GB places, where there is an indoor environment and we want to monitor the physical distancing, I think it violates user privacy. And that's why even we have a trade-off between the privacy and performance. Okay. So the proposal here, or what we propose in this paper, is to explore, okay, the thermal sensor array towards physical distancing measurement, and we also try to find the distance between the sensor to human using artificial neural network. We also, regarding some numerical values, we got a median overall error, 20 centimeters for unseen testing data, completely unseen data. So the aim, again, just to emphasize, is to have a physical distancing system. But the objectives of that is we need to segment the human from the low resolution image that we obtained from the data collection. And then we need to count them, because we want, for example, we want to measure distance between people. So we want to estimate the occupancy. We need to count the number of people in the scene. And the third objective is the sensor to human distance. And we will explain why this is important in the next slides. And then we can find the physical distancing between people. If there is any breach of social distancing policy, a trigger will be alert. We will come to these phases one by one in my next slides. Okay. So the thing is that the importance of this work is a privacy preserving. So it provides a privacy preserving approach for the physical distancing. And this is the sensor that we use. It's a very small, low cost sensor, and it does not need to people to wear it. Like, it is not a wearable device. It is not a mobile that you need to wear it wherever you go. And it has a high refresh rate that can capable to detect swift human movement. And that's actually very important in a human-centered application. So this is again, if you see this slide is again, this is actually the abstract of the human segmentation and equivalency estimation of the first objective that we have. Just to remind you that the low resolution thermal sensor is not like a camera, because this is an image that the first image here is actually the image that we collected using from a vertical placement from a wall, and this is from the ceiling in the second image. So the idea in here, what we want to have is, we want to have a framework that capable to segment the human presence regardless their shape, regardless the placement of the sensor, in what we call adaptive thermal sensor array placement for human segmentation, and then count the number of people in that scene. To do that, we propose a framework, okay, that based on a deep convolutional encoder-decoder network for human semantic segmentation. So as I just said, maybe the shape of the human from a ceiling statement differs from that human shape if we collect it or we obtain the thermal image from the wall. And that's why what we want to have is not a detection. We want to have a semantic segmentation to classify each pixel in the image into either human or background. And that's why we propose kind of, again, some set of pre-processing and post-processing techniques that suit this type of sensor, the low resolution sensor. For example, because this is actually a very low resolution, the output of the sensor is a very low resolution image. So we try to make kind of a heat map interpolation by 3, just to make it a better resolution, to make the thermal images a better resolution. We try to also to have another maximum temperature boundary, the second box here. And this is just to filter, for example, imagine that a human carrying a cup of coffee. This is a noise that we want to get rid of it. So any abnormal human temperature, we remove it, and we convert it to the minimum temperature in the thermal scene. And then we convert this heat map into RGB image. Just a quick note in here, the heat map itself that we acquire from the sensor is matrix, rows and columns. Each row is a temperature. So if we want to visualize this, we try to use color map called JET, and then we can visualize this scene in red and blue colors that you saw earlier, okay? So that's why because we wanted to use it with semantic segmentation, we convert this heat map into an RGB image. Now we have 3 matrices, RGB, okay? And then we did another post-processing technique. Like, for example, sometimes because of semantic segmentations, we have some errors. For example, some pixel could be identified as foreground, but the error from background. So we used some connectivity filters. We just did another extra human presence validation just to see if there is another human in the scene that could disappear because of the color map that we used. And then after we locate the human presence, we know the human in the image, where the human is in the image. We try to make the recovery of the human temperatures because we don't want to lose them to estimate the equivalency. So these are the illustrative results of our adaptive thermal sensor array placement for human segmentation. For example, the first image in here is a human from a sensor obtained from a ceiling placement with the first two, and as you can see, it was able to semantic segment their location. Okay. Similarly, for a human at far distances or from vertical placement, we were able to identify their to segment their presence in this low resolution thermal scene. Okay. As I said, we are calling it as a privacy preserving because from these images you cannot know or you cannot tell the identity of the person in the images. Okay, that's why it's a privacy preserving approach, because no identifying information can be obtained out of it. So our occupancy, we also did some kind of comparative results between our work and some of the state of the art. And in our work was adaptive placement compared to other work that uses the same sensor, thermal sensor array. Some of them combined with the BIR. I don't see any reason why they use BIR because it is the same temperature. So some of them using ceiling, wall, and our work was using wall and ceiling. We can see even in the adaptive boost, we use a classification to estimate the occupancy, to count the number of people. We have 98.43%, shallow neural network 93.75% from the wall position. From the ceiling position, adaptive boosting was 100%, and from the ceiling, shallow neural network was 58.33. Anyway, we have a good performance in adaptive boost algorithms, and this is again comparable with the state of the art results. Plus, it is adaptive, so you can deploy it wherever you want. So you don't need, for example, to tell your technicians this sensors only work on the ceiling of the elderly person. You can take this sensor, and now it is the decision of the technician. He can put this sensor wherever he thinks it is suitable, on the ceiling, on the wall. It is like a camera where you ask the technician to place a camera in a public place. We wanted to have a system that can the technician decide on the place where he's working, his workplace, decide where he put the camera, the thermal sensor array, and our system should work with his or her placement accordingly. So now we move to the sensor human distance estimation. So as you can see from this image, okay, the human shape itself, because this is again low resolution thermal sensor array, you can see now even this is actually from a half meter, and when you go far from the sensor, the shape is different. So we have some. So this is actually just to visualize, for you to visualize what is the output of this sensor using female participants and male participants. From a distance of half meter to 6.5 meter. So from from the images that we saw earlier, and these images, we can see that thermal human presence is affected actually by the human distance, sensor to human distance. This is actually explains what I said. So even in here, it is at 9 meters. We cannot really know that this is a human presence or not. Or even if the placement has a role in here. If it's in the vertical, we can understand, oh, this is a human. But from the ceiling, it could be a chair. We don't know. So again, this is kind of the human shape differs even from the sensor placement, and on the like the human distance and the sensor placement affected what the output of the human presence in the thermal sensor array output. So because of this problem, we want to avoid the high variation of the human presence. What we suggest to use is the temperature values. Okay, we want to estimate the human distance, right? So to avoid this high variation in the human shape or whatever, or the human presence, because of the factor that we explained earlier, we try to see, for example, how the temperature drops, within the distance, and we can see the maximum, minimum temperature, and the average temperature, the median of temperature and variance are kind of increase when the distance increase, or decrease when the distance increase. Okay. And therefore, we try to use this feature to estimate the occupancy. So we, for example, collected some data every half meter step, and we try to classify. Okay, we want to classify. So we have, for example, if we have 6.5 meters every half meter, then we have approximately 13 class, right? So we want to classify, so we divide our data set to classify where the human is. Is it class 1, class 2, class 3, class 4? So class 4 represent 2 meters. But this is not really the ideal approach. The ideal approach, we want to have a continuous estimation. For unknown data, we don't want a class system. If the person is located wherever in the field of view, I want to have a distance like 2.4 meters. This is actually what we want. That's why we call it continuous distance estimation, and that's what we use where it was in this paper. So the first discrete continuous distance estimation was for comparison purposes, just to see, is it just by luck we got a good result using continuous distance estimation, or it is proven that it is working, so using discrete or different classification algorithm as well. So once we identify the human to sensor distance, now we can identify we have different scenarios of physical distancing. Person can be placed here, the other person can be here, they could be horizontal, they could be even in more complicated scenarios, someone in here, someone in there. So we try to use some geometric information to find the distance passed on their location to each other. But one important question in here is, what I'm saying is, okay, for example, in this picture, we don't know each pixel how many meters or centimeters represents, right? Because so we cannot measure the distance without knowing this one. And that's why what we done is we try to find, for example, So can be found, for example, in here is the inspection area. So the field of view at each distance, what's the inspection area? So if we identify the sensor to human distance for the first human subject is 2 meters, then we try to use this formula, which is 2 multiply the sensor to human distance, 2 meters, multiply tan of field of view and divided by 2. So what's the field of view in here? The field of view of our sensor is 55 degrees multiplied by 35. So by using this formula, we can now know, okay, what is the depth, what is the distance between the human and the sensor, and based on that, we can use this formula to what? To know M. And then we can interpolate each pixel, how many centimeter represents, and based on that, we can use these scenarios, this geometry information to find the physical distancing between human subjects. So the continuous estimation results, our results, is actually the data set that we collected divided into 2 subsets. The first subset is actually the thermal data obtained at the decimal distances, for example, half meter, 1.5 meter, 2.5 meter. So this is the first subset, and this subset used to train the neural network. The second subset is actually a completely unseen data. So which is actually 1 meter, 2 meter, 3 meter, 4. So completely measurement, completely a new measurement. And we try to what? We try to test our trained neural network. So the median overall error was plus minus 4.2 meter. And for comparison purpose, we tried to use to see, again, as explained earlier, the classification algorithms for different class. Each class label is a distance step, okay? And we found that QPXL SVM has an accuracy of 96.8%. And this is actually just to make sure that we don't have overfitting problem. We try to use cross-validation faults during the training and testing stages. We had also done some robotics, for example. Okay, we identified that this sensor can work from the wall. Okay, so we tried to use our neural network, the trained neural network. Okay, where when we put the sensor on the ceiling placement. So our network, artificial neural network, is not trained to predict the distance from the ceiling. It is only trained to predict the distance from the wall. And we were able to achieve a median error of 0.07 meter for male participant, which means that it is even better than from the vertical position, from the wall position. But for female, the error was 0.66 meter. It is not too bad, but I think the female participant in our experiment, and this our validation experiment, was wearing a head scarf, and I think it reduces the temperature, her head temperature, and that actually was kind of why we had some kind of 0.66 median error for the female participant. We also try to propose a kind of a new transfer application. We have this neural network, okay? So why not to use it in a new application, which is to measure the human height? And that's why, and how can we achieve this? If the ceiling, okay, if the distance from the floor to the ceiling is known, then we can use the proposed neural network to predict the distance between a human and the sensor. And then we subtract them from each other, we know what the human height. So this is a transfer application, and which shows the importance of our work, and not only in the physical distancing, but also in predicting the human, or predicting or extracting the human height, physiological features from these low resolution thermal images. We also try to propose a new feature, which is actually to classify the field of view where the human is. Is he near the sensor? Is he in the medium range of the sensor, or is he far from the sensor? So what we did in here is we try to look at the pixel, like if we have the sensor on the wall, we try to see the bottom pixels in the image, and we can see, like, we can see what? We can see when the human goes far from the sensor placement, he moves up. So the bottom pixels, the background pixel and the bottom pixel are increasing. So if we count, for example, the bottom pixels, non-human pixels, and we use this as feature, we could then classify the field of view, where the field of view, into 3 classes: near, middle, and far regions, where based on the human presence. And this is the confusion matrix, okay, of our work, and we can see a very good results again for using this feature to classify the field of view into 3 classes. Okay, if in some application we don't need really to know where the exact human location, but we want to have a very quick real-time system that can tell us if the human is far or near or in the middle. So we can use this feature to do this. So the conclusion of this presentation, what we propose is a privacy-preserving, low-cost, and non-contact physical distancing measurement framework. And the proposed approach was able to estimate the distance for a discrete and continuous estimation using classification and neural network accordingly. A transfer application using the proposed distance estimator is introduced to extract physiological human features. And future work could be conducted to fuse, again, multiple sensors together to cover a wider inspection area. And this is actually a very important future work. Yeah, this is me, and this is the last slide. Thank you very much for listening. If you have any question, if you would like to contact me further to discuss maybe anything, of course, you can ask me during this session, but also you can also contact me via email. You can even search on my name using LinkedIn, ResearchGate. You can contact me. I am always happy to connect with the new people, expand the network, and of course, we look forward to receiving your comments or any discussion, collaboration in the future. Thank you very much. That's all from me for now.
Thank you, Abdullah.